Hello? You guys in the back hear me good? Sure. All right. So my name is Tyler Kelley. I'm a graduate student at UCI, and today I'm going to be presenting my work on called Elvis at the Disco, kind of a sort of branch from Shay's previous work, embedding desks in the Milky Way simulations. So this is work that I've done with Shay, Garrison Kimmel, Mike Bolin-Cochin, and there we go, James Bullock. So just to give you a brief refresher on what it is we're doing, that's not supposed to be there, but there's the punchline. If you compare dark matter only simulations to hydro simulations, in this case the fire simulations, you see that on large scales, it's kind of covered up, they're mostly the same. But if you zoom in towards the inner regions near the hosts, they start to become significantly different. And the motivation behind this project was, how can we recreate this difference without having to run a hydro simulation? And the technique that we came up with we called it an embedded potential. So you just take a sync particle, and you put it in the center of your dark matter only simulation, and you add little kicks to the dark matter particles around it based off of the accelerations from a time-evolving potential. And then you do all of this inside a cosmological simulation. And so how well does this work? Well, it works pretty well. On large scales, not really much, but on small scales, you recreate the effect that you see in the hydro runs. So what Shay did was he tuned his Milky Way, or his disks, to be matching the latte simulations, and he only had 2. And so we wanted to improve upon that. So I matched explicitly to the Milky Way as best as I could today. So I wanted things to look like the Milky Way and grow into the Milky Way as it appears today. Then I wanted to improve upon the embedded potential that we used so that it more matches an exponential disk. Then include more components. So Shay only included a stellar disk. I wanted to include gaseous, stellar, and a balls component. Slightly increase the mass resolution by almost a factor of 2. And then sort of the important point here, increase the sample size to include 12 halos spanning the sort of Milky Way uncertainty mass range from 0.8 to 2 times 10 to the 12. And this is the Elvis disco simulations. So how does this work? Well, at the interior of our halos, around 100 kiloparsecs, we see that there's a significant suppression of about a factor of 2 within the halos, and it's pretty much mass independent. It's pretty well happens to destruct all halos across various mass ranges. If we change our focus to the radial distribution of these subhalos, we see that there's the overall suppression of a factor of 2 within 100 kiloparsecs. But then as you start to get into the center, you see that there's about a factor of 10 reduction within about 30 kiloparsecs, and then there's almost nothing within 20 kiloparsecs. So you may ask, well, that is only for things that are today, but you can look at the paracenter distributions of the halos that survive within the 100 kiloparsecs, and you see that compared to the dark matter only simulations, the disk simulations has nothing that survives to today with a small paracenter. So things that pass close to the center of the disk are the ones that get destroyed. So that's all simulation data, but sort of an important result that just came out was the Gaia data release 2. And so you can compare our data to the pericenters that have been derived from the Gaia data. The Gaia data and the dark matter only line looks pretty terrible. But if you compare it to the Milky Way satellites from the Gaia release, it's pretty hard to recreate that data without matching the simulations. So I want to take a little bit to talk about the stream heating, so the radial profile that we saw. So why is stream heating important? Well, when an object interacts with the stream, it leaves this distinct signature that should be easily detectable as long as you can stare at a stream for long enough. And then this is important because it will allow us to detect these dark substructures, so things that don't have stars in them. You should be able to detect them, and then as Gaia will continue to produce data, it should allow us to detect these things in streams. The problem is that there's basically nothing that's going to be there to do the stream heating. So that's a problem. In addition, it's not just that today that there's nothing there. It's actually that if you look at the number of subhalos within a 20 physical kiloparsec radius of the Milky Way throughout time, there's been a distinct lack of substructure there, and so there hasn't been really any chance for any interactions with streams. So then, just kind of like a spotlight here, the introduction of having a disk potential shifts the median infall time by about 1.6 gigayears, so things that fall in early in the age of the universe are going to get preferentially destroyed. Okay, so now that we've talked about infall times and destruction of satellites, let's talk a little bit about the missing satellites problem. So the standard missing satellites problem is kind of pictured here. The observations of Milky Way satellites that we see we see much fewer Milky Way satellites than we see in our simulations. But that's not really a problem because we can say that, well, these are very small subhalos, so most of them are going to be dark through reionization and cooling and whatnot. That's not really a problem. So we can say, well, if we want to match this radial profile, what do we have to do? What sort of cut do we need? We say, well, if we want to match them, it looks like we're going to need a peak cut of 10 kilometers a second, which is pretty small, but we'll just keep going with it. Then this is only using the dark matter only simulation, but kind of the whole point of this is that you can't do it with a dark matter only simulation. You need to include the disk. So if you do that, then you get a profile that doesn't match what we observe. So now you definitely have a problem. If we wanted to match the profile, V-peak cut of 10 is not quite going to get us there. So play the same game. What do we need to match the radial profile? Say, well, actually, we're going to need to go back to V-peak of 4.5, which is incredibly tiny. These, we just said, had to be dark. You can't form any stars in them. So now we have a problem. There's definitely a big mismatch there between the two. So in summary, the central subhalo count is drastically reduced by about a factor of 10 basically within the inner regions. The stream heating signal that you should be able to detect through Gaia or whatever means is going to be incredibly low because there isn't anything within that inner region to do the stream heating. The pericenter distributions that you get from including the disk are the best match to the Gaia data release proper or pericenter values, and there's potentially too many ultra-faint satellites, and James is going to talk about it a little bit later, so if you have questions about that, you can save them for him. And then finally, infall times are shifted slightly later, or I guess not slightly later, actually significantly later by 1.6 gigayears. And finally, my catalogs and merge trees will be made public very soon. Thank you. Yes.
So if you do out into this, that you may be disrupting way too many satellites. And these very idealized studies that were intended to try to shock you, we didn't seem to be strong enough to actually disrupt all of anybody from A to Z. Don't worry about a similar effect here, or do you think that you increase the time shocking so much that maybe it is accidental?
For the satellites that pass very close to the disk, I don't think it's a problem because the satellites, they're going to get disrupted. They just disappear, essentially. Yeah. So that's definitely something that we're looking into because this is the region that we're examining is the sort of problem area that he specifies. And so that's something that we're trying to be very careful about and definitely keeping in consideration. But yeah, I haven't made any plots of that, no. But yeah, that's something we should look into. Oh, so the surviving satellites, the cutoff basically was 20 kiloparsecs for present day satellites.